Let's take a look at the process of adding rational expressions. This first example is an example of two rational expressions, but more simply, these are just fractions. Fractions are a type of rational expression. And if you've worked with fractions before, you may recall that to add them together, I need a common denominator, because the denominators tell me what the numerator kind of means. It gives us sort of a basis for judging the size of the numerators. So if the denominators are different, I can't really compare the two numerators. And to add the expressions, what I'd like to do is add the numerators together, but I can only do that if they are equivalent, if they have the same denominator underneath. I can adjust the fractions by multiplying the top and the bottom by the same number, and I want to find a multiple of both of those numbers that would allow me to turn them into the same thing. So one way to approach the problem, we could just list the multiples of each of those numbers. I mean, if the numbers aren't too crazy, I could just start with 8, and then 2 times 8 is 16, 3 times 8 is 24, and I can think of it as adding 8 each time. 4 times 8, if I add 8 more, I get 4 times 8 is 32. 40 is 5 times 8, 48, and 56. I could go through the list. I don't want to go too far before I maybe go over and look at 10. So 10, another 10 would be 20, 30, 40, 50, and but wait, we don't need to go much further because 40 works. 40 is a multiple of both of those numbers. And so, if we think about it, 40, it came from 8 times 5, and it came from 10 times 4. So if I multiply 8 by 5, to keep everything the same, I need to multiply the top by 5 as well. 3 times 5 is 15. 5 times 8 is 40. And so the fraction 15 over 40 is the same as, it's equivalent to the fraction 3 over 8. Because, the reason why that works, 5 over 5 is just equal to 1. So essentially what I've done, because I multiplied the top and the bottom by 5, essentially we multiplied that fraction by 1. Over here, to turn 10 into 40, I can multiply by 4, but then we also need to multiply the top by 4. And so I end up with plus 4 over 40. And now, when the denominators are the same, I can simply add together the numerators. 15 plus 4 divided by 40, divided by that common denominator. And 15 plus 4, of course, those are like terms. Those are just numbers. So I can put them together. I get 19 divided by 40. And so that's our final answer. A second example I'd like to look at, involving variables. Of course, rational expressions can involve variables. And so I might have an expression like 5 over a plus 2 over a squared. In a similar way, I can adjust those fractions to create a common denominator. In this case, the a and the a squared, well, a squared, we know, is just a times a. And so if I multiply this a with another a, it'll turn it into a squared. And so I can multiply the 5 up top by a as well, to keep it the same. So I'm multiplying the top and the bottom by a, so that overall I'm just multiplying that whole expression by 1, and we get 5a over a squared plus 2 over a squared. So now I can add together the numerators, 5a plus 2, just like we did with the fraction example over there, divided by a squared. But now, that's it, right? Because I can't combine those because the a, 5 times a, and the 2 aren't like terms. They aren't similar because one of them has a variable and the other one doesn't. Also, let me point out, I can't cancel things because a is not a common factor. So the a that's up top, it doesn't cancel with the a squared in the denominator. That's an easy mistake to make. But because of that plus sign, the a up top, it's not multiplied with everything else, and so I can't cancel it with a squared. A third example that puts sort of those two parts together, where I have now numbers that are a little bit different and variables that are slightly different in terms of the exponents. Let's see what we can do with that. So here I need to create a common multiple for both of those numbers, and I could list the multiples like I did for 8 and 10, but I want to mention another approach that we could take. We could look at the prime factorization of those. So 25 is 5 times 5, and 5 is a prime number. 35 is 5 times 7, and 7 is also a prime number. So I can't really split those up into any smaller parts. So looking at those two prime factorizations, here for 25 I don't have a 7. So if I multiply 25 by 7, that'll make it look more like 35. It'll include that factor of 35 that 25 doesn't have. And also 35, it's divisible by 1 5, but 25 is divisible by 2 5s. So I should multiply 35 by 5. And both of those calculations give us 175. So 175 is a common multiple, and it's the smallest common multiple of those two numbers. So I can turn the numbers into 175 if I multiply 25 by 7 and 35 by 5. For the variables, well, here I have z cubed, and here I have z squared. So if you think about that for a moment, I need to multiply the z squared by one more z. So in terms of the fractions, let me write this out here. So I have z plus 7 over 25z cubed. For that first rational expression, I want to multiply the top and the bottom simply by 7. I'm using parentheses here because I want that 7 to multiply both the z and the 7 up top. For the other rational expression, 1 over 35z squared, I want to multiply the top and the bottom by 5 to turn the 35 into 175, and also by another z to turn the z squared into z cubed. But then of course I need to multiply the top by 5z. So let's do that. If I multiply across, I get 7z plus 49 over 175z cubed plus 5z divided by 175z cubed. So now I can add the numerators together because the denominators now match. I can add the numerators. I get 7z plus 49 plus 5z divided by that common denominator that we found, 175z cubed. And we're almost done, but there is one more thing that we can do. There's one bit of simplification. The 7z and the 5z, those are like terms. They both have the same variable raised to the same power, and so I can put them together and write this a little bit more simply as 12z plus 49 divided by 175z cubed. So for that last example, adding z plus 7 over 25z cubed with 1 over 35z squared, we end up with 12z plus 49 over 175z cubed. So I'd like to look at one more example and maybe suggest, take a moment, pause the video. This is a slightly, tricky is maybe not the best word, but this is a slightly different example. A little bit subtle maybe is the word. Pause the video, think about what could you do to turn those two denominators into a common denominator. And then that would allow us to put the numerators together. So x and negative x, if I think about these denominators, the tool that I have to work with is basically multiplying the top and the bottom by the same thing to make the two denominators match. The only difference between those is that one is positive and the other is negative. But I can change that if I multiply, and it's a little bit simpler, if I multiply the second denominator, the negative denominator, if I multiply that by -1, then let's think about what happens. If I multiply that by -1, then this just becomes positive x. I didn't do any changes to that first rational expression. This becomes a positive x, and 1 times -1 is now just -1. So I can put those two things together. I have 2 plus -1 over the common denominator. I don't want to change that denominator. I just make my denominator of the answer x. Of course, 2 plus -1 is the same as 2 minus 1, so I just have 1 over x. I hope you enjoyed the video. Thanks for watching.